Hey guys. Again, my name is Paul. I work for HKS in Dallas, Texas. And I wanted to say thank you very much to the organizers for having me here. I've not had the opportunity to attend this conference before, so I'm looking forward to the next couple days. HKS has made a name for itself over the last 80 years for being able to deliver very large and very complex projects. And over the course that we've been in business, the definition of what is a complex project is something that has been constantly changing and evolving, starting out with the introduction of CAD and then moving into the world of BIM. And although the definition of BIM is, it's fairly open-ended, we find that at our office, we are gravitating towards a BIM workflow that uses Revit primarily. But the essence of that phrase, building information modeling, is something that we try very hard to keep in mind. How do we make use of all of this information at our disposal to not only document great buildings, but also design them in the first place? So I'm going to talk a little bit about how we approach that question at our office, and then show you guys some of the work that has been produced because of that. So within HKS, I work for a small team, and it goes by the name of LINE. It's an acronym. It stands for the Laboratory for Intensive Exploration. And we try to bridge the gaps that we see between our firm and the world of academia and then the industry as a whole. And we are effectively HKS's applied research and development team. We operate as a bit of a hybrid between a traditional architectural design team and then a consultancy. And in that sense, we spend about half of our time designing our own projects, and then the other half helping to solve very specialized problems for other teams within our office. And these problems can vary in complexity, everything from energy modeling and environmental simulation to complex geometry creation, and then getting into specialized applications development. And at that point, we're writing our own software when it's necessary. And the question that we get an awful lot is, why is that necessary? Like, why would you ever need to do those things? And indeed, most of the work that we do is capable of being built out of fairly regular construction assemblies. This is a project that I worked on a few years back, and this is the definition of a complex project. This is Fort Hood Replacement Hospital in Killeen, Texas, and it's roughly 1 million square feet. We had 30 or so subconsultants, and it took us like 4 to 5 years to finally get it off the ground, and it just opened recently. But this followed a workflow that was very repeatable, and after we got everything figured out, it was actually, it's actually quite efficient. And so this works great, and the only problem is that occasionally we like to design projects that look like this. And then that workflow is not quite as clear-cut as it was in the last project, and there's not like a whole lot of dimensionable things going on over here. What we have is a lot of very complicated geometry that's going to need to be very carefully communicated to the fabricator. And then we're going to have to figure out how to build this as a kit of repeatable elements so that it's not just astronomically expensive. So within HKS Line, my role is that of a computational designer, and that means that I use computer programming to manipulate data during the design process. And that data sometimes is geometry, but it doesn't necessarily have to be geometry. And if you are building shapes that twist and curve like this, it makes sense to build them as a relationship of elements within the computer rather than as a fixed modeled object. So that way, as the design changes, you don't have to rebuild everything. But the real benefit of this type of workflow is not being able to make twisty, curvy shapes, although it is really fun, and we do it a lot. But the real benefit here is being able to make things talk to one another that might not have actually been able to do that before or never been designed to do that. So I'm going to focus on that primarily here. And so you guys are familiar with the new Vikings Stadium. What you might not be as familiar with is the genesis of this one, and this actually started out looking a little bit different. It started out looking like this. And my team produced one of the initial concepts for the design phase, and it's actually cool. Some of the final elements made it all the way into the built project, the big rotating doors at the end zones, and then the ETFE clear panels, although they're being used as part of a structural clear story. But this project stands out in our mind just because of how fast we were able to do it. We did this entire thing, including the renderings and everything, in about 4 days. And it was by no means a perfect process, but we were able to define a very clear design direction and then add a very large amount of supporting detail quite quickly, purely through scripting. So everything here is being done in, this entire model is being built in Grasshopper. All of the elements here are basically being derived off of a series of 6 input curves that can control each one of these roof sweeps. And Grasshopper is a plugin for the Rhino 3D modeler. It's very similar to Dynamo in many respects. The coolest thing about this project to me was that those roof slices were not random. I mean, this was very deliberately produced in order to optimize the amount of natural daylight that was going to be falling on the playing field. We wanted this experience of playing football outside to be preserved, and we also wanted to make sure that we could block any direct glare from the players and for the fans. And so to do this, we hooked up the geometry of the model to a radiance-based daylight simulation. And this was the first time that we'd actually been able to do this on a project. It's not uncommon to be able to build something and then simulate it, or build something and run an energy model on it. But to actually make use of that as part of the design, and as you change something, you get instant feedback. That was something that we've been trying to do for a while. And this is actually what excites me the most about the possibilities of computational design. It's what I specialize in within the Line Group, and that is using the results of various simulations to iteratively influence how the design is going to finally progress. And so this video looks complicated, but it's actually a relatively simple way to explain how that works. So what we're doing here is I'm providing a series of simulations and then linking them to the creation of geometry to answer a question. So right now I've got a very small volume. I've given it the ability to rotate back and forth, add and remove windows and all the different facades, and then also mess with the shading on the outside. And then using something called a evolutionary solver, the computer looks at each frame of these simulations. We've got a useful daylight study and a solar radiation study, and useful daylight is described as daylight that's neither too bright nor too dark. And then for each option, it's going through and plotting the results up here in the left corner, and using an evolutionary solver, the computer can then start to understand which combinations of all of these parameters will go together to provide the best results. And you're in charge of defining what the best results actually are. So here I'm asking it to minimize the amount of radiation that's coming into the building and then maximize the amount of daylight. And so, it starts off bouncing around a little bit, but overall, it starts to gravitate towards a solution that is favoring northern light and then shading and minimizing the amount of light that's coming in from the south and the west. And this is something that makes sense intuitively. We would try to do this on our own, but the computer's actually figuring it out mostly by itself with a little help from us. And so obviously this is answering just one question out of a nearly infinite number of questions that you could be asking while you're designing a project. But the takeaway is that we try to use the computer for what it's good at, which is crunching numbers repetitively over and over again. And that frees us up to think more holistically about the design. How can we make buildings that at a base level are more responsive and more sustainable? And so to see what that looks like on an actual built project, this is San Francisco International Airport. This is one that we're almost finished with. And we were brought in on the design side at the very early stages, and then after the project was secured, we became a consultant again. And here we were trying to figure out how to unify the workflow between the design architects and what ended up being a small army of sustainability engineers. As this is San Francisco, they're very interested in the sustainability of the project. And so what we were trying to do is look at every single design change that we would make to the geometry and then see how that would play out in the overall performance of the building. So this chart is showing how work would flow from HKS, the design architects, which were HKS and Woods Bagot, and then flow into our mechanical engineers and our sustainability engineers. And again, using Grasshopper as the intermediary between all of these different platforms, we were able to take each design option and then very quickly run a life cycle analysis that's being depicted here, courtesy of Arup Engineering, and then also go through a conceptual level energy model as well as a passenger comfort evaluation. And then for things where we wanted to get into a little more specificity for certain systems, that's where those evolutionary solvers come in. And this one in particular is trying to figure out if the building can qualify for the LEED V4 daylight credit. And this is obviously a small area for demonstration, but what it's doing is it's choosing shading options, and it's running the series of LEED V4 daylight studies, which is spatial daylight autonomy and annual sunlight exposure, and then charting the results, again, finding out which ones will qualify. I'm also defining a couple things in the upper left-hand corner here that we're also trying to look at, which is bringing the shade area down to minimize the costs, and then also switching out various spectral profiles of the glazing so we can see how that impacts the quality of the daylight. And Lawrence Berkeley Laboratories out in California has a fantastic database of pretty much every glass type that you could ever run into in North America, and so we're testing out some of our favorites there. And the beauty of this is that you can start to, you can look at so many more options that you would normally have time for given a compressed schedule, and then you can take the options that meet both the aesthetic and the performance options that you're looking for, or performance criteria that you're looking for, and you can take them to the client with a very high degree of certainty that what you are providing is best for the scenario. This next project is Kuwait Children's Hospital. This is the only pediatric, or will be the only pediatric care center of this size in the Middle East, and it'll be one of the largest ones in the world when it's done. And while SFO was mainly focused on optimizing certain systems with analyses, with this one we wanted to use those same tools to provide more input in the design of the facade itself. One of the key design drivers for this project was that of a healing crystal, and you can see that language reflected in many areas of the interior and the exterior. And so we started with this crystalline triangular grid for the facade, and then developed a tetrahedral shading option and gave it the ability to twist and rotate with two goals. The first was to obviously respect the program underneath the shade, but then be able to provide a very clear view to the Persian Gulf, which is right outside the window. And the initial idea was to modulate the screen and the pattern very aggressively with the program changes. And that could look something like this, where we have a fixed number of pieces that are then kind of arrayed in patterns across the surface. But the client really gravitated towards an option that faceted sympathetically with the podium and ended up looking something like this. And so for each one of those macro facets that you can see here, we provided a tuned shading module that did both of those things. It reduced the amount of insulation on the surface, which in the desert is a big deal. And we're able to maintain as clear of a view to the Gulf as possible. We also looked at the feasibility and payback of renewables. In this case, photovoltaic arrays, both standard as well as BIPV. And there is a chart that you can look at that will tell you the optimal orientation of a solar panel at any given point on the planet. But again, we used an evolutionary solver here to drill more specifically into our building and our context and start looking at things like row spacing, with rotation and building overshadowing, and making sure that it makes perfect financial sense to put these panels where they go, because they are quite expensive. And then at the end of the day, none of this really matters if you can't take all of that information that you've developed and studied and learned and apply it back to your final product, which as architects, usually that's a drawing set. And this project, because it was so large and spread out, we had teams working simultaneously on 3 continents at one point. We chose to use the Flux interoperability platform as a hub for all of our conceptual design information. So this is a screenshot of the Flux web interface, and we're creating all of our grasshopper models and all of our simulations, and we're throwing them in here as a repository, and then we're able to pull out the stuff that we need and we want to go into the documentation model. And so here you're seeing that same series of points being brought in, and we're developing the adaptive components that are going to be making up the majority of the skin. In fact, 80% of this building is made of adaptive components that are automatically being generated off of that grasshopper data. And the black window here in the middle is a Python scripting window. And the reason that we have that is the API of Revit is so large, it's massive. And Dynamo is still a relatively new way of looking at it. So oftentimes what we want to do with Dynamo is not actually set up to do that just yet. So we find that we're writing a lot of nodes to push and make that transition a lot more seamless. But the end of the day is a fully functional Revit model that is then directly connected and linked back to our simulation information. And this is a fully connected workflow. So if someone makes a change in Grasshopper, it gets iteratively pushed into the Revit file, which is quite helpful because at the 11th hour of the 100% CD phase, I was still making pretty drastic changes to this facade based off of some new material information that we had on our simulations. And I would not have been able to do that. It would have been pencils down a lot earlier without this kind of workflow. So it helps in situations like that. And so, we've been speaking about documentation challenges, and we go back to the Viking Stadium again. This is actually the project that inspired a lot of the workflows that I've just gone over in the last few slides. Somewhere in the middle of the design process, we realized that, in the documentation process, we realized that some of the surfaces, of the macro surfaces of the stadium were actually curving in more than one direction. And this became apparent and became more of a problem as we tried to document the skin in Revit, because as you know, if you've used Revit, it really does not like twisting surfaces. So we went through several studies trying to reconcile putting a flat panel on a non-flat surface. And seeing if we, seeing how we could actually do that. So this is one of those studies. This is a growth algorithm that I wrote again in Grasshopper. And what this is doing is it's taking a fixed panel and then it's arraying it up the design surfaces, and it's trying to float the rotation and the tilt within the construction tolerances of the panel system, which I think in this case was like 1/8 of an inch or something, just to see if we could actually physically build it. And that produced something like this that we could use in our documentation model, but there were still some serious concerns about how we were going to build it. And thankfully, working together with Thornton Tomasetti Engineering and Mortensen, we were able to figure out how to get these mapped properly, and they did a fantastic job of applying all the panels in the field. I mean, it looks quite good. So after Vikings, the concept of rationalizing non-uniform geometries into repeatable parts was something that we took a big focus on, and it's a process that we use quite a bit. We're using it currently on the Los Angeles Rams' new football stadium, which unfortunately I'm not allowed to talk about today. We're also using it on this, and this is a development in Saudi Arabia at the heart of Jeddah Project. And each of these blue design surfaces is going to be made out of interlocking triangles. And right now in the design model, there's roughly 30 to 40,000 of them, and they're all completely different sizes. And so we've developed a rationalization algorithm that goes through and tries to bring that down to a more manageable number. And in this case, we're able to go from that many thousands down to just 5 different shapes. And the process that makes that looks something like this. So we're now very firmly in the world of computer programming, and the goal here is to now create one piece of software that can obviously help with the design, but we're really trying to just skip the documentation process entirely and then take that file straight to fabrication and then start interfacing and writing G-code for the robots that are going to start building and machining all of these different parts. So to sum up everything, these projects are taking us in directions that we would not have anticipated before we started. And we've found that the ability to remain flexible with our workflow is one of the most important things that we have going for us. And we like to remain platform agnostic, which is a phrase that I'm not sure who coined, but it's a really good one. You find something that works for 90% of the stuff that you do. And for most of the work that our office does, Revit is the only tool that we actually need. But there are some projects like these that need a little bit extra. And on these, we're writing completely new tools, mostly from the ground up, to get those concepts actually pushed into reality. Thanks.